Hello, everyone. It's 1 p.m. here in Colorado, and it's time for an Econ seminar. Welcome to the 2023 Econ Seminar Series, and thanks for joining us. It's an honor and a pleasure for me to introduce to you Dr. Xueying Yu. She's a postdoc at Stanford, and she has a PhD in Land and Atmospheric Science from University of Minnesota, Twin Cities, and a Master of Science in Meteorology from Nanjing University. She studies atmospheric chemistry, greenhouse gas emissions, satellite remote sensing retrievals, and carbon mitigation using inverse modeling and other data-driven approaches. And specifically, her research focuses on quantifying methane emissions from point source level to the global budget. And that's what she's going to talk about today. Before starting, I'd like to remind you that you can enter your question at any time during the seminar in the window below, and I'll read them out loud at the end of the seminar to Xueying. And with that, please take it away.
Thank you for the introduction. So hi everyone, thanks for being here, and thanks for the invitation, and thank you for the opportunity to let me present my research. I'm Xueying, currently a postdoc at Stanford working with Professor Rob Jackson, and my research is mainly focusing on quantifying greenhouse gas sources, especially for methane. Today, I'm going to present the research that I did during my PhD study when I was in the University of Minnesota working with Professor Dylan Milley. It is characterizing methane emissions from point sources to the global budget. In the beginning, I would like to thank my collaborators, co-authors, and for their contribution. So why would we study methane? Methane is a very crucial greenhouse gas. It contributes to more than 65% the relative forcing of carbon dioxide. For example, shown here in the left, this is the effective relative forcing from IPCC AR6. It shows the global warming contribution from each species relative to their emissions since 1750. We can see that the carbon dioxide, which may be more familiar to most of us, makes the largest contribution, followed by methane. Methane is a little bit more complex than carbon dioxide because carbon dioxide is very stable in the atmosphere, so that the effective relative forcing is contributed by carbon dioxide itself. But for methane, it will react with OH, generating ozone and other VOC species. Those other species can also be important greenhouse gas, so that the effective relative forcing for methane shown here include not only methane, but its oxidation production caused by those methane emissions. However, this does not indicate methane has a secondary importance to study because it has a strong global warming potential. At 20-year timescales, global warming potential for methane is 85 times of carbon dioxide, and methane has a short lifetime. It is 9 years, comparing with the 100 years lifetime from carbon dioxide. Such short lifetime and strong global warming potential offers great benefit to study decarbon for methane, because with effective decarbon strategy, and if lucky enough, maybe we can be the generation to see a decrease of methane concentration. Maybe it can be even decreased to the pre-industrial time. At the same time, methane is also an important precursor of ozone, which is air pollution in the troposphere. This links methane with air quality. Methane is also an important fuel, so that if we can effectively collect methane in the atmosphere, those can be very useful. Despite all those importance to study methane, we know little about its increasing trend. Shown here in the right, this is methane-methane ratio in the atmosphere date back to 2000 years. Today's methane level is around 3 times of its level since its pre-industrial time. It is especially mystery in the recent decade as the zoom-in plot. The methane concentration in the atmosphere first increased since 1980, then reached a relatively stable stage at around 2000. After around 2006, the methane in the atmosphere continued the rigorous increase, and the reason of this relatively stable stage and the regrowth remain unclear. In the recent years, we have an accelerating increasing trend for methane, reaching around 20 ppb in the past year, with reasons that are still unclear. With all those uncertainties, so how well do we understand the current methane budget? This is a global methane budget in the past decade from the Global Carbon Project. The two values listed here, the first one is a bottom-up estimate, which is such as based on statistics, such as how much methane is emitted per cow times the cow population. The second value is a top-down estimate. It is quantifies the methane budget based on atmosphere observation. On a global scale, there are more than 150 teragram per year discrepancy between those two estimates. Methane emission can be from fossil fuel production and use, agriculture and waste, biomass burning, wetland, and other natural emissions. The largest contributor for this top-down and bottom-up discrepancy is from the other natural emission, especially for the inland water. Well, the uncertainty in the methane budget is not only in the emission, but also in the global sink, the reaction with OH. If we combine the bottom-up emission inventory and the current methane sink estimate, it implies around more than 100 teragram per year change in the atmosphere burden, which is a 6 times of the 13 teragram per year observed growth rate. This indicated a large gap in our understanding of the global methane budget. With such large uncertainty, the global totals are best constrained. There are even large uncertainties in regional or sectoral emissions. For example, shown here are two sets of bottom-up inventory for the North American methane emissions. Both of them are believed to be the state-of-the-art emission estimate, while the only spatially correlated to R² equal to 0.26. So here we are going to discuss the contemporary methane budget and diagnose the causes of those discrepancies. I'm going to talk about 4 projects from the point sources, which we use aircraft measurement to quantify key facility in the Midwest, then to a regional and Midwest regional constraint. After that, I'm going to move to satellite. We first characterize the challenges and capability of current satellite data to map methane sources, and then map the global methane sources based on the real methane data from TROPOMI. In the beginning, I'm going to start with the point source quantification. I'm going to focus on agriculture and waste, which account for more than half of the US anthropogenic methane sources, especially focus on the concentrated animal feeding operation that can host thousands of animals in a limited area and dominate the US animal production. To do that, we designed the aircraft measurement from GEM flight. This GEM flight has 2 purposes. The first one is to quantify the key point source in the Midwest, which we quantify the 9 of the largest animal facility and 2 sugar plants. The second purpose of the GEM flight is for regional quantification, which I'm going to explain that later. Shown here, those are the flat tracks colored by methane concentration, also the locations of those key point sources. This aircraft is the one we use for our winter flight. A flight is performed by scientific aviation. Onboard instruments include Becquerel to measure methane, ethane, CO2, and water vapor. Also include aerodome for CO2 and water vapor. We also have instruments to measure ozone. The air inlet is installed in the right wing, and instrument is installed inside of this aircraft. Most of the time, the aircraft will fly within 1 kilometer above the ground to measure methane concentration simultaneously in the mixing layer. For those point source quantifications, the aircraft would spiral up and spiral down for those facilities for both upwind background methane and downwind background plus plume methane. Then we integrate those methane concentrations horizontally and vertically to arrive at the point source emission estimate. For comparison, we design a bottom-up emission estimate for those livestock. We use EPA emission factor times the animal population. For the sugar plant, we use the facility report to the greenhouse gas reporting program. Comparing this top-down aircraft flags and the bottom-up emission estimate, we found for big facilities which is dominated by enteric sources with little seasonal cycle. Those aircraft measurements shown here as a red dot. It agrees very well with the bottom-up estimate indicated as a black line. However, for the dairy emissions, which has a large contribution from both manual and anthropic with strong seasonal cycle, we found those aircraft reveal a significant bottom-up overestimate. Well, if we compare the aircraft measurement with the green line, which indicated the anthropic only emission, the two actually agree very well. But for those hub facilities, the aircraft indicate one overestimate and one underestimate for those two facilities. And for sugar plants, which dominated by waste sources, the aircraft reveal dramatic bottom-up overestimate with potentially biased seasonality. So that at pore source level, our aircraft measurement indicated around 40% to 80% bias in the methane emission estimate. And then I'm going to move to the regional scale, which you will find that the pore source finding is also consistent with the regional scale analysis. At the regional scale, we use the data from the same flight, from the GEM flight, to quantify the importance of the up Midwest for the national budget. This is a very crucial area as circled here. In the left, this is a graded EPA inventory for U.S. agricultural methane emissions, include both methane manual management and anthropic fermentation sources. Even though it is in a log scale, we can still say that the upper Midwest stand out for its extensive agricultural activities that include more than 700 million livestock and the majority of the U.S. hog facilities. In the right shown here is a wetland for U.S. wetland methane emissions from wet chart inventory. And the Midwest is among the two most wetland-rich areas of this country. This is also the prior emission estimate I'm going to use for the inverse analysis. In our study region, most of the agricultural sources is located in the south, while the wetland sources is located in the north. This offers great benefit to separate emissions into sector level. We use the GEM flight to quantify the methane sources. Also, we use the data from other flight and Tall Tower in this framework. This is a summary of all those data. The three boxes shown here in the left for the small black box is the region of the GEM flight. The middle red box is the region we analyze the methane flux, and the large blue box is the region we perform the model simulation. We use GEM to quantify the methane sources, and those are the flight tracks that we already seen. And across the Pacific Ocean, those are the atom flight, which we use to optimize model boundary condition. For other model belts, we use IGRA radio sound to evaluate the model planetary boundary layer height. In our evaluation, the belts caused by the model mixing layer is within 10%. Finally, we use the independent data from American flight and Tall Towers as independent evaluation of the inverse result. Our inversion based on the GEM flight can successfully improve the model simulation of those independent data. Due to time limit, I'm not going to show those evaluation. And our inversion is relying on the cost function shown here. It includes two terms. The first one describes the state vectors optimizing emissions, the deviation to the prior estimate, weighted by the prior error. Well, the second term describes the observation and the model simulation mismatch, also weighted by the observational system error. Our model aims to reduce this cost function to arrive at a point that has a best balance between the prior estimate outcome, which can also fit the observations to the model simulation. Our INS framework includes three major components. The first one is a sector-based analytical inversion with a fixed spatial distribution for the prior emission estimate. The second one, we use Gaussian mixture models to spatially cluster grid cells prior to optimization. And the last one, we use GEOS Chem adjoint model to optimize methane emissions at 25 kilometer scale. For those inversion frameworks, they yield as a consistent methane source adjustment. Shown here is for 3 seasons, the sector level scaling factor. The scale factor is an optimized emission divided by its prior estimate. So if it is higher than 1, that means emission is underestimated. Lower than 1 means the emission in the prior is overestimated. In this plot, each row indicated one inversion, which is sensitivity cases that optimize boundary condition as well. And each column indicates one sector, including total emission, livestock, wetland, and others. We would like to point to two key messages. The first one is a bottom underestimate of livestock flux. It is underestimated around 25% in summer and winter, but within 15% in spring. I'm going to explain this later. For the second one, we would like to point out a bottom-up overestimate for spring wetland flux. It is underestimated by around 35%. If we look into a more local measurement, this is an eddy covariance measurement also from our group made by Julian and other folks. It is consistent with the flight inverse analysis result. Shown here is a time series of the eddy flux. The black line shows the eddy flux estimate, and the blue box is a white chart which we use as the prior estimate. For many years, such as 2011, 2012, and 2014, we see a later than predicted wetland emission onset. And one hypothesis we think is potentially relying on the lag between surface skin and the soil temperature. The surface skin is what used in the white chart to predict the onset of wetland emission, but the soil temperature may be more related with that onset. If we look into more details of the wetland emission, this shows the spatial distribution of the optimized emission and the optimized minus prior emission from the GMM inversion. Other inversion also give us consistent and comparable results. We found emissions underestimated in the northwest region, which is a prairie plateau region with a highly variable hydrologic conditions influenced by snow, rainfall, and underground water. But wetland sources are overestimated in the Great Lake coastal region, where hydrology is relatively consistent, mainly influenced by the Great Lake. Looking into the drivers of those emission correction, we use the white chart ensemble model. It estimates the wetland emission based on diverse assumptions, including 3 temperature dependencies, Q10 is equal to 1 to 3, and also includes 3 scaling factors to scale the regional wetland emissions consistently. Also include 2 wetland distribution, either from GLWD or globe cover. This shown here is a Taylor diagram of all those ensemble from white chart inventory comparing to the observed, which is the optimized methane estimate. In this plot, each point indicates one ensemble case, and the distance between each point to the observed point is the root mean square error to the optimized flux. The slope to each point to the original point indicates a spatial correlation of that ensemble case to the optimized case. We found that in terms of the wetland extent, the GLWD cases yield an emission overestimate, which is shown here indicated by color, but it has a higher spatial correlation with the optimized flux than the other dataset. In terms of the temperature dependencies, we found that when Q10 is equal to 3, it yields the lowest root mean square error in our region. Then moving back to livestock emissions, we found that manual measurement is still a key uncertainty. This is consistent with the point source analysis. Similar as previous slides, shown here is a livestock optimized emission and optimized minus prior emission. We found livestock emissions are underestimated across seasons, and the magnitude is summer higher than winter, higher than spring. This is the first evidence indicates manual measurement is a key uncertainty because entry fermentation is relatively consistent across the year. For the second evidence, we then aggregated the emission correction into animal category based on the beef, dairy, and hog population in our study region. We found for beef facilities, which mainly contributed by enteric sources, the emissions are well quantified within 15% in the bottom-up inventory. But for dairy and hog, which has a higher fraction from manual management, the emissions are underestimated by around 30% in summer and winter, but well quantified in spring. The spring, a lower scale factor may be caused by manual is applied to field in that season. With that, we present the optimized methane budget in the Midwest. Wetland is the largest regional source, and the livestock is the largest and the progenitor source. One interesting thing is we further evaluate the potential use of widespread use of the anaerobic digestion, which can collect the methane from livestock facilities. There are around 4.5 kilogram per year methane mitigation potential in this region. That is around 2 times of the total methane emission from the entire Permian Basin, which is believed to be the largest oil and gas methane sources in the US. Thus, in the regional scale, we quantify the importance of the Midwest and highlight the substantial mitigation opportunities. Then move to a broader scale, we're wondering if we can scale up our funding from flight to a broader scale based on satellite data. So in the beginning, we quantified the capability and the challenges of using current generation and next generation satellite to map the methane sources. We use TROPOMI as an example of the current satellite. This illustrates how TROPOMI observing the Earth. TROPOMI is really fantastic. It offers an unpredicted opportunity with around 7 kilometer pixels near daily over land coverage at 13:30 local time overpass. The methane measurements from TROPOMI include short-wave infrared and near-infrared informations. We present an observing system simulation experiment to evaluate the capability and the challenge in using TROPOMI data to map methane sources. To do that, we use 2 sets of bottom-up inventory, one as the prior estimate, the second one as the true emission. They only spatially correlated to S greater to 0.26. In the true emissions, we use the GEOS Chem version 11 to perform the true simulation, then add the instrument noise, arriving at the synthetic observations. And the inverse analysis is performed in GEOS Chem adjoint model, which has a forward model from version 8. So the transport error is introduced in this LC by performing the inversion and true simulation in different versions of GEOS Chem. We also perform another set of LC where the prior emission is equal to half of the true emission to evaluate the effect caused by the spatial pattern belts from the prior emission. Our LC include 1 month of observations to evaluate if those 1 month TROPOMI synthetic observation can effectively correct the prior belts. So we have 2 focus. The first one is the transport error influence. The second one is the spatial pattern belts in the prior influence. This shows the initial gas minus prior minus true and the optimized flex minus true emissions. First, this is showing the most clean case without transport error with a spatial accurate prior. The label here is the regional belts reduction and the spatial correlation to the true flex. We found the inversion can improve the emission estimate at 25 kilometer scale in those cases. However, when we have a spatial inaccurate prior, at a regional scale, the inversion can still improve the emission estimate. But the missing sources are misalligned to large nearby sources. For example, in the south of Hudson Bay, those sources are missing in this region, but instead of scaling them up, the inversion turned to allocated 4 sources in the west to compensate for a concentration underestimate in the downwind region. But when we have transport error with a spatial accurate prior, the large sources are overcorrected to compensate for the transport error. When we have both transport errors and spatial inaccurate prior, the inversion can only achieve mineral belts improvement. To solve this issue, we develop alternative inverse framework. Because one reason we think for this limitation of classical scale factor relies on the scale factor itself. Because in the base case scale factor is times with prior as well as optimized. So if the prior is very low near 0, then no matter how large the scale factor is, it cannot effectively scale up the prior emissions. So that we develop other strategies such as using flat prior or combine a background increment with the bottom-up inventory, or use observational gas from tropomids and add it with the prior. Finally, we design a framework to optimize emission enhancement, where the emission correction is added to the prior rather than scaling the prior. As you will see later, the enhancement framework gives us the best performance to identify the missing sources. This shows the performance. X is the Dauman weld belts, Y is the spatial correlation to the true flux. So the best performance will be the top corner of this dashed line. In this plot, each point indicates one inversion with different time frames and different framework. With a spatial accurate prior emissions, we found those inversions can improve the emission magnitude at 25 kilometer scale. And when we have an accurate emission model transport, additionally, observations can progressively improve the spatial emission estimate towards the top corner of the dashed line. Well, when we have a spatial emission error and transport error both present, either of those inversion framework can improve the inversions. Results are strongly degraded. So in this OC, we characterize the challenges and capability of tropomy to map missing sources and develop new inverse frameworks. So combining all those inverse frameworks can give us an opportunity to diagnose the accuracy of our optimized emission spatial pattern. Finally, I'm going to present the real global methane emission estimate based on the tropomy satellite data. This shows the 2 years tropomy methane observations over sample to 0.1 degree. We can see it reveals very important source fingerprint for methane, such as concentration hotspot over California near Mississippi River, in the Central Africa, in the Middle East. Those in the Middle East might relate with fossil fuel activities. Also, those concentration enhancement over South Asia. Next, I'm going to use GEOS Chem adjoint model to interpret what are the sources that contribute to all those concentration enhancement with the same framework that we designed in the previous OC. And our inversion implies a distinct methane budget. This is very surprising to us. We have two treatments of the methane sink. One is using the prior OH from GEOS Chem version 5 as a consistent constraint. Another one is optimize the OH concentration with methane sources. So in the second one, both methane sink and sources will be optimized. Shown here in the red is an optimized methane simulation from the fixed OH and the optimized OH cases. Those two yield a consistent simulation. Both of them can successfully improve the model bells. We also evaluate the fixed OH and optimized OH based on independent data set from OPSPEC. Also, both of them can successfully and to a same magnitude to improve the model simulation bells from those independent data. But those two inversion indicated distinct solution as shown here in the left. X is a global methane emissions, Y is a global methane loss, and each point indicates one inversion solution. The size of the point indicates the Bell's reduction in independent data from OPSPEC. Those fixed OH converge at a higher global flux, while the optimized OH converge at a lower global flux. To further evaluate which case is more reliable, we then turn to other species using airborne measurement of OH and CO from atom flight. We perform this evaluation for atom 1 to atom 4 across 4 seasons. But shown here is for the atom 1 because other seasons also give us comparable result. Shown here is the latitude variability of OH and CO, as well as their data density. The black line is the observation, blue is the prior estimate, red is the optimized OH. We found that for OH, the prior estimate of OH actually agree better with the observed value. And for CO, which also the major sink is reaction with OH, the optimized OH is overestimates the CO sources, overestimates the CO concentration. so that those independent data from atom OH and CO support the solution of the fixed OH. This is very surprising because in the optimized OH, we optimize both OH and methane sources, which has a higher degree of freedom. So one might expect it give us a better solution. But instead, the fixed OH actually agree better with those independent OH-CO measurement and also can successfully improve the methane simulation. Therefore, it indicates that optimizing methane source and sink simultaneously only based on methane observation is a little pose problem, even using the dense tropomi data coverage. As shown here, the prior OH can give us a very good simulation for CO and OH. Thus, I'm going to focus on the fixed OH solution in the following. Our optimized global methane sources is 588 teragram per year, which is the largest contribution from wetland. Shown here in the red is the global methane emissions and the global emission correction to the prior estimate, which is from the bottom-up inventories. We found emissions are overestimated in the North Hemisphere high latitude region, but underestimated in the tropical and subtropical regions. This is the result at 2 by 2.5 model grade. We further develop a spatial downscaling approach to downscale those 2 by 2.5 solution into 0.1 degree. This equation explains our downscaling is relying on two assumptions. The first one is a higher tropomi over samples indicate a larger probability for methane sources. The second assumption is a larger prior emission estimate indicated a higher probability for emission correction. I'm not going to detail explain it here, but if you're interested for this downscaling approach, please reach to me. Thank you. We evaluate this spatial downscaling based on the Aussie. Of 1 month Aussie over the North American, we first perform the Aussie at 2 by 2.5 scale, then apply this downscaled approach as shown here as a downscale solution. We also perform this Aussie at 25 kilometer scale in the GEOS Chem adjoint model, shown here as a fine-grade adjoint solution. When we do not have transport error, those two solutions can both improve the domain weld emission belts and can also improve the slope of this square feet. But when we have transport error present in the Aussie, the downscale solution can still successfully improve the domain weld belts, while the fine-grade adjoint solution have limited improvement. This is also presented as previous in our previous auto study because of the spatial pattern belts and the transport error limited the fine-scale adjoint solution. Another benefit of this spatial downscaling is the faster computing, because the 2 by 2.5 inversion already take us around more than 12,000 CPU hours to converge. So the inversion rarely performed at 0.1 degree would be physically impossible. But this spatial downscaling approach can give us a comparable emission estimate at a very fast manner, with additional benefit of mitigating the transport error. This spatial downscaling approach enables us to look at the emission hotspot globally. Shown here in the left is the emission increase estimated by Edgar bottom-up inventory in the past decade. The color indicated the emission increase magnitude. Shown here in the red is a hotspot correction from the fixed OH. The color indicated whether emissions are overestimated or underestimated in the inversions. We found a crucial region of the underestimated hotspot is in the Middle East and South Asia. Those emissions underestimated in the Middle East are related with the fast development of fossil fuel activities, and they are consistent, and the emission corrections are consistent across the year. While the emission correction in the South Asia has a seasonal pattern. Shown here is the optimized minus prior emissions for the South Asia for each month from May 2018 to October 2019. We found most of the emission correction is during monsoon season from July to August, while for the non-monsoon season, the emission corrections is minimal. This emission correction starts as a Bangladesh region following the monsoon onset in July, and then extend to the entire northern India. And the emission correction diminished and shifted eastward in October following the monsoon withdrawal. During the entire monsoon season, there are around 10 to 13 teragram methane emission increase over the South Asia. We think one potential reason or driver related with those monsoon emissions might related with monsoon rainfall, because the monsoon rainfall will increase the water extent, then increase the methane emission from wetland, also from waste, livestock, and rice. Thus, on a global scale, we investigated key knowledge gaps in the global methane budget with a focus of atmosphere oxidation, which we found that optimizing methane source and sink simultaneously only based on methane observation itself might be low post even using the dense troposphere data coverage. And we also interpret the drivers of unexpected sources. In particular, we identify the underestimated hotspots in the Middle East and South Asia. With that, I'll try to present my take-home messages. So we look at the methane sources from point sources to the global budget. At point source level, our aircraft measurement reveal around 40% to 80% bells in the methane emission estimate for the major livestock and waste operation in the US Midwest. Then move to the US Midwest regional scale, we quantify the importance of the Midwest in the national methane budget. Based on the optimized methane sources, we found substantial mitigation opportunity that up to 4.5 teragram methane reductions can be possibly achieved through widespread use of the anaerobic digestion. Then we move to a broader scale based on satellite observations. We design our observing system simulation experiment with two focuses. One is to explore the transport error influence to the satellite-based inverse analysis. The second one is to explore the spatial pattern belts in the prior estimate to the inverse performance. We characterize the challenges in using the high-resolution satellite sensor to map methane sources and develop new inverse framework for improved identification of the methane sources. Our OC highlight the careful to the transport error and the combination to the spatial pattern error in the prior, because when both of those errors present, the satellite-based inversion might have limited improvement to the emission estimate. Finally, at the global scale, we investigated the key knowledge gaps in the global methane budget with the focus of the role of atmosphere oxidation and the drivers of unexpected sources. For the atmosphere oxidation, our inversion indicated that the optimizing methane source and sink simultaneously based on methane itself might be low post. And for the unexpected sources, we identified the underestimated hotspot in the Middle East and South Asia, which might related with fast development fossil activities in the Middle East and the rainfall from monsoon in the South Asia. And my current postdoc study also building on those studies that I did in my PhD study. I'm currently developing a multiple species inverse analysis, not only based on methane, but also based on the methane oxidation chain, such as including formaldehyde, CO, and methyl chloroform. Also using the Bayesian inverse framework. And thank you for your interest. With that, I will be happy to take any questions.
Thank you so much, Xueying, for the great presentation. Oh, we already have a question. That's great. South Asian monsoon season also coincide with rice crop growth season. Do you think that could be an important contributor apart from the wetlands in this region? Thank you, Rajesh, for the question.
Yeah, thank you, Rajesh. I think it's we indeed think both the wetland and the rice crop growth might be an important contributor to the emission correction during monsoon season. Also because the rice crop growth region is coincident with monsoon. And one driver we are thinking is both of them are based on hydrology, because rainfall from monsoon can increase both rice emissions and both wetland sources. Yeah, thank you for the question.
Okay. Let's see if we have another one. Well, maybe we wait for another one. I was wondering when you were showing the Midwest measurements, how much the frozen soil is sort of limiting emissions in the winter, and how much the shortening of the winter season could impact those emissions. Do you have an idea? Have you thought about that at all?
Yeah, in the bottom-up inventories, they are currently using the surface skin temperature to predict the methane emission. And during winter, when it's lower than a certain temperature, it will set the emission to be 0. And so in the current bottom-up inventory, most of the winter season in the Midwest, the wetland sources is treated as 0. But there are indeed wetland sources during winter measured by the ID flex measurement in our group. In terms of the shortening of the winter season, this is really an interesting topic, especially under the background of global warming. We might expect the winter season is shortening and the temperatures increase during fall or spring. That might increase the methane emissions. I'm not very sure how much methane emission might be increased during this season, but that would be very interesting to study.
Yeah, thank you. Thanks for a great talk. Can you say more about the impact of model resolution on inversion result? Thanks, Helen, for your question.
Yeah, thank you. Thank you for the question. I'm thinking both of my previous observing system simulation experiment and the real triple mean measurement, real triple mean inverse analysis. Because in the OC, we perform the model simulation at 25 kilometer scale, which is a really fast scale, and we found the model transport error plus the spatial biased prior error can lead to a very limited emission estimate improvement. But when we perform the spatial downscaling, where when we first perform the inversion at 2.5, we found on that scale, because on that scale, the bottom-up inventory has a better spatial pattern accuracy than even with coupled with the transport error, the inversion can have a better improvement of the regional emission estimate. So I guess it really depends for the model resolution and for the inversion solutions. On one aspect, with a finer model resolution, we can have a better, have a finer spatial pattern for the optimized emission. But on the aspect, with the model transport error at a finer model resolution, we might have a limited improvement for the regional source quantifications. I don't know if I answered correctly.
Okay, Miruz, thanks for your question. Thanks for the talk, he says. And do you also see any seasonal differences over the Middle East?
In our inversion, we performed that across 2 years. We use troposphere data from 2018 to 2020, but we interpret our inversion from May 2018 to October 2019. Across this time frame, which is 1.5 years, we did not see any seasonal difference over the Middle East. All of the seasons, there are strong emission underestimate in the Middle East. Especially when we compare it with the bottom-up inventory, that the major source in the Middle East is contributed by fossil fuel activities, which is rapidly increasing in the past decade. So for the fossil sources, we might think it might not influenced by a seasonal pattern. But I'll be very interested to know if there are some seasonal pattern in the future years are quantified by other sources, quantified by other studies.
Okay, very good, thank you. Eric asks, well, compliments for you for your talk, and maybe asks, maybe you said so and I missed it, but what do you believe is the larger driver of the methane increase in the last 15 years? And can isotope measurements help inform our understanding?
Oh, that's a very good question. Thank you. In the past 15 years, there are really many hypotheses to interpret the drivers of methane increase, such as some might say a decrease of OH, the major methane sink. Some might attribute it to the fossil fuel activities. Also, especially for those studies using both ethane and methane, using ethane as a secondary tracer to quantify methane sources from oil and gas. They identified many methane underestimate from fossil fuel activities. And there are also current isotope studies to interpret the carbon-13 measurement that indicated a lighter isotope source signature in the atmosphere, which indicated a larger contribution from biogenic sources, such as from wetland and livestock. Some study might combine those, thinking both the fossil fuel activity and the biogenic sources contribute to the methane increase in the past decade. I think it's still something remains to be studied. And in terms of the isotope, can isotope measurement help inform our understanding? Of course, isotope measurement, it can be very useful. I think for isotope measurement, it can quantify for two things. The first one is for methane sources, because the biogenic might have a lighter isotope signature, and for the biomass burning might have a higher isotope signature. So looking into the isotope measurement can help us to aggregate the methane sources into sector level. On the second thing, the isotope, due to the kinetic effect, it has a different reaction rate with the OH and also with other methane sink. So it can also help us to look into not only methane sources, but also methane sinks. I'll be very interested to look more into the isotope.
Okay, we get another question. Great presentation. Have you tried a joint inversion using both the flyover data and the satellite data? For example, using the inversion results from one type as the prior for the other, or some other schemes? Thank you for the question.
Yeah, thank you. We indeed thinking about that. When we move from the regional scales and Midwest based on the aircraft data to a broader scale of satellite, well, we were thinking how do we combine the aircraft data and the satellite data. To be honest, we did not do that in the last because it's really depending on how we set up the inversions, whether we put more weight to the flight data or put more weight to the satellite data. I'm thinking if we can explain it in this way, those aircraft data might point to one solution of the regional methane sources. So satellite data might point to another set of solution, and how to combine them is depending on how we set the joint inversion. It's depending on how we set the regulation parameters. And yeah, that's the thing that made us not do that starting the last. And in terms of the example you listed here, using the inversion solution from one type as a prior for the other. This is also a very good point. I'm also curious if we can use the optimized flags from aircraft to the satellite, if that might change our solution. In our aircraft data, we try this strategy a little bit, that we first use a Gaussian mixture model to optimize a sector level methane sources based on the aircraft data, and then followed by a GEOS Chem adjoint simulation, followed by a GEOS Chem adjoint inversion to optimize methane sources at 25 kilometer scale with the prior as the optimized flags from the previous Gaussian mixture model inversion. And it can indeed improve the inversion result. Thank you.
Okay. Mariam, thanks for the great talk. I was wondering if the dust storms in the Middle East can impact methane concentrations. Very interesting.
Yeah, that's very interesting. I don't know too much about the dust storms, but I'm wondering if those dust storms can influence the satellite retrieval, might cause I'm thinking about two things. The first one is if those dust storms can influence satellite retrieval, that cause observation bells, which might lead to bells in the inverse analysis and also in the following interpretations or in some other studies that's not using the inverse strategy. The second thing I'm wondering is the driver of those dust storms. If the climate change on some aspects lead to more intense or less intense of those dust storms, if the same climate change things can influence activities, human activity, and also other nature sources of methane in that area. That's a very good question. I will be more looking forward to discuss with you more maybe after that.
Okay, let's maybe wait a little bit. In the meantime, I'll ask you a curiosity of mine. Are you planning any measurement campaigns down to Florida, Southern Alabama, and those? Because that's another hotspot. It looked like from your map, right?
Yeah, that's another hotspot. It's very good for California. It has fossil fuel activities and also it's another center of livestock facilities. But as a postdoc, I don't design any flight now. My current postdoc study is still using the inverse analysis in the GEOS Chem adjoint model to interpret still the triple satellite data for more recent years, and we have a different focus than my previous study. At this moment, we more focus on the drivers and on a sector level to interpret the methane sources. For my previous study during my PhD, I more focus on both the emission sources and the emission sink, the methane sink. I hope to design some flight.
Okay. Well, thank you so much. It looks like we're done with the question. Thank you so much for your great talk and for your answers. Thanks everybody for the great questions, and see you in 2 weeks.
Thank you. Bye.
Bye-bye.